With this, we are starting chemistry of elements, and we are starting it with hydrogen, the simplest element, the simplest atom that sits at the very top of periodic table. Usually we say it belongs to group 1, which is natural, it has only one electron. Some people would say it belongs to group 7 to the same extent, but this is nothing to discuss. It's a very special element. It has properties different from anything else. To start with, main compound on this planet containing hydrogen is water, H2O. Element itself exists in form of diatomic molecule, H2, which boils at around 250 degrees negative Celsius and freezes at even lower temperatures, still being H2 molecule, the only form of hydrogen we know. Hydrogen has two stable isotopes. Because of high importance, second isotope of hydrogen, having one proton and one neutron, we named deuterium. So, formula of dihydrogen with two deuterium atoms will be simply D2. There is also unstable radioactive isotope with two neutrons, which is tritium. In nature, slightly more than 0.01% of hydrogen is deuterium. Example, natural water. Completely deuterated water can be obtained from natural water by distillation or electrolysis. The reason is that boiling point of heavy water, D2O, is slightly higher than usual water. So by fractional distillation, you can obtain D2O of very high purity. The same is true for electrolysis. How we can synthesize hydrogen atom, the hydrogen molecule? In industry, there is a large-scale production of H2, and the cheapest at this moment is production from natural gas or alternatively from other hydrocarbons. The reaction is CH4, methane, reacts with water at very high temperature and nickel catalyst, making carbon monoxide and 3 hydrogen gas molecules. Now further, we can run so-called water-gas shift reaction. Water-gas is mixture of CO and H2. And this is carbon monoxide reacts with water to give carbon dioxide and one more hydrogen molecule. As a result, you have CO2, which can be relatively easily separated. Actually, it freezes at a relatively low temperature, and you have pure hydrogen gas. Alternatively, instead of hydrocarbon, you can use coal. So carbon from coal reacts with water to make hydrogen and carbon monoxide. A little bit of oxygen is added so the process will be self-sustainable. Its temperature will raise simply because of heat released by coal combustion. So formal reaction is much simpler. C plus H2O, CO plus H2. Now this again is water gas. So we are running water gas shift reaction, making CO2 and H2O exactly like it was before. In laboratory, it's much easier to receive hydrogen by reaction of metals or with acid, or different metals or with sodium hydroxide, aluminum with sodium hydroxide, or zinc, or with HCl. Hydrogen is sometimes produced and consumed in the same industrial process without being separated. As an example, in Haber process for the production of ammonia, we do not have hydrogen. We take natural gas, produce hydrogen, separate it from natural gas, and then run production of ammonia using the same setup. Another industrial procedure for synthesis of hydrogen is electrolysis. It's more expensive at this moment than synthesis from hydrocarbons, but very promising because of possible storage of energy. If you consider hydrogen as possible fuel, you're running electrolysis using electricity from some natural sources like wind or solar energy and make hydrogen, the storage. Most common is electrolysis of sodium chloride, a very important industrial process that results in sodium hydroxide, yes, we need it, chlorine gas, again we need chlorine gas, and hydrogen. So there are three products of these. All of them have industrial importance. You can use different electrolytic setup for different electrolysis reactions, making hydrogen and then storing it in liquid or compressed form.